Okay, so today we're going to take a look at stacks and queues. So stacks and queues is a advanced data structure. Okay, it's also called a abstract data structure. Just like the linked list, it has the ability to grow and shrink dynamically as the program is working. But it seems like it does a lot of what the linked list does. But what I want to talk about now is this advantages of hiding features, hiding data from programmers and from sort of the problem-solving process. So the fact that you can hide stuff, make stuff private, we can do that with variables, we can do that with data structures, we can do that with methods, we can make them public or private, hide them from inside or outside the class based on the design of what you're trying to construct as a programmer. Okay? The fancy word for this is the sort of interface that you're creating with your code. The abstract data structures often hide some of the features of the program itself from outside. So for example, in our linked list that we were working on, we made a method called findNode. But it was just a little private method within the class. The other methods inside the class used it, but if you were outside the class, you wouldn't know that this method called findNode existed. Okay? So we hid it. So we're going to see that when we develop some of these ADTs. And the three big ADTs that we're going to look at are the table, the stack, and the queue. The table specifically, we're going to look at something called a hash table in that. Okay, so if we imagine what the table would do, as a structure, okay, we would need to insert things into the table. We'd be able to delete things from the table. We should be able to search the table, and we should be able to output or print the table. Very similar to the linked list. Those are very common features. Okay? Now, a table can be something as simple as a 2D array, but it could also be something more complicated, and that's the one we're going to look at, is something a little more dynamic. But today we're going to focus on the stack. The stack object is a particular object that always adds things to the top and removes things from the top. So the best analogy is like a stack of dirty dishes, where when a new dirty dish comes in, you put it on the top of the stack, but when you go to wash a dish, you always pull it off the top of the stack. So this is what's called a LIFO structure. That's the acronym, which means the last one into the stack is the first one out of the stack. We're going to then later look at a different object that has a different structure to that. So for example, we could set the bottom of the stack to a null pointer so that that would indicate that we're at the bottom. Okay, so here's the animation. So when you add something to the stack, it always piles on the top of the stack. But when you remove things from the stack, you remove it from the top. So this one here at the very bottom of the stack was the first one in. It'll be the last one out. And this one, which was the last one in, is the first one out. Okay, and that's why it's called the LIFO structure. Okay, so that's the stack object. So here's what we're going to need to be able to do to create this thing. These are the methods we're going to write. Obviously, we'll write a constructor so we can build the stack. To add items to the stack, the word we're going to use in methods is push. And to remove it, we're going to use the word pop. So we push onto the stack, and we pop the stack to remove it. We'll also write a little method to just take a quick look at the top of the stack without actually removing it. We'll make a little isItEmpty method and one to determine the size of the stack. Okay? Now we will do this through inheritance of this big linked list class that we've been building. But as well, I will later show you an example of code how you could build the stack from scratch. Okay, so now I'm going to set this up in NetBeans. So I'm actually going to build a brand new project. I know you guys already have the project, so just indulge me for a sec. So I'm just going to make a Java application just called grade 12 code example 2014. Okay. And get that set up. So one of the things I showed you guys last time, and I'm going to put on this video, is this idea of organizing to the next level. The idea that we started our organization when we started learning about coding by organizing our code into methods. And methods are great, right? They allow you to dissect your code into separate parts. Once we got past that, then I also taught you how you could then also separate your code into classes. Okay? And classes is really the key to good programming as an object-oriented programming language, is building and designing objects and classes that really separate your logic into more usable chunks. Now I think you guys are there, and now we're going to go to the next level, which is this idea of creating packages. Okay? That's the icon that NetBeans uses. It represents a package. Packages are ways to essentially separate your classes so that they can have similar names. In other programming languages, they are called namespaces. So you can have different namespaces and therefore use the same object of the same name within those different namespaces. But in Java, they call them packages. But at a simple level, it's just another way to organize your code. So as I said last time, the easy way to do this is just right-click and go New Package. And one I suggested was the one called Collections. Okay? And then I also suggested one called Databases. Okay? So when you create these packages in Java, they will be available in NetBeans, and it'll demonstrate them as little package icons. If they have nothing in them, the package will be gray. When it has a class in there, the package will be yellow, I guess, yellowish color. So again, what I suggested last time was take the linked list code that we worked on in our previous example and copy it into the collections package. So now your collections package will contain the linked list that we spent all that time working on in the last unit, and obviously for the linked list to work, it also needs our node class. So that's now part of our collections. And the other one I suggested we do is for the databases, take a copy of the file handler, the file handler class that we worked on in the unit before that. So this has kind of now collected some of our useful classes from the units. And again, we're going to kind of always use this project now to do our examples. So now, having that in place, I'm going to also rename this package. And what did we call it? I'm trying to remember exactly what we called it. I think I just called it something like main package or something like that. Something simple. Okay. And in there, I'm just going to rename this file just main class. Okay, so now I've added a level of organization to my code here so that I have packages to separate some of my stuff, and within the packages I have classes which separate. Within the classes I have methods and data structures, much more organized. And now we can start building a stack object. Okay, so I'm going to new Java class. I'm going to call it the stack. Now as you build a new class, watch out right here which package it's being inserted into. That's an important distinction. So you can always shift it around, but now I can add the stack to my specific package. This now explains this line of code right here, what that line does. So that line that we often ignored now tells us which package this class is a part of. As well, when you use a class from a different package, it will import it based on that name. So the import statement will now include that. Okay, so now we're ready to start our stack. And here are some of the methods that we're going to need. We're going to need the constructor. We're going to need a public a public void push method that takes t data. And it's going to push it onto the stack. Now, the stack uses generics. So we're going to add the generic t up here to indicate that this stack will use generics to work. But we're not done yet. In addition to being generic, we are going to extend the linked list. Okay? So this top line of definition of the class will say that a stack is a linked list. Okay, so it maintains all the abilities of the linked list, and it deals with generics. Okay? So we will have a default constructor, so we can build the stack. We have a push method that will add objects to the top of the stack. We will have a public tPop method that will remove, and let's just have it return null for now. We'll fill that in later. Remove objects from the stack. We'll have a public tTop method, which doesn't remove objects from the stack, but looks at the object at the top of the stack. So just have it return null for now. So push, pop, top. We'll have a public Boolean isEmpty method, which for now we'll just have it return false. We'll do that in a second. And a public int size method that for now let's just have it return 0. Okay? So this is what I said we were going to do with our stack. That it would be very simple. It wouldn't have all the features of the linked list. We're going to hide most of them. Size, isEmpty, top, pop, push, and a constructor. 6 methods. Okay? So it reduces what the linked list can do. Okay? So maybe I mentioned this word to you guys before. It's a kind of a buzzword in computer science. It's called skeuomorphism. Skeuomorphism is this idea that you take real-world objects and create software that mimics the real-world objects. So for example, you could get an app on your phone that looks like a 1970s rotary dial phone. Right? So it's trying to morph that environment through software. So again, kind of what we're doing in that is you're reducing the functionality to create an interface for the user that's something that they're maybe a little more comfortable with. Now that's not the case here with the stack. We're not reducing the functionality because programmers don't want to know what a linked list is. We're reducing it for specific programming purposes, that the stack's lack of abilities will create abilities for itself, that problem-solving things that we normally wouldn't think of. Now I'll get to that later. We can write this stack quite easily. The lines of code to fill in all these methods are actually very, very simple. To construct a stack, all I need to do is construct a linked list. What will be the line of code to do that? Well, it's the superclass. So I'm going to make a call to the superclass, and that's it. To construct a stack, construct the superclass. So it would go to the linked list class. Hang on. And it would find its default constructor, and it would run that code. And we've already done that. So that's all it takes to construct a stack. Now, we'll skip pushing and popping and top for a second. We'll get to those last. isEmpty. Well, in our superclass, we actually already have an isEmpty method. So we can just return the call to super.isEmpty. Now this will prompt you that this seems like this is a override taking place. And it'll prompt you to add the override, which is fine. That's exactly what we're doing. We are overriding our superclass with our own method. It happens to be the same method, but that's what we're doing there. Okay? And size is a similar function. I returned super dot, and for that one, we called it length. So I've changed the name slightly between length and size, but it's the same idea. I just make a call to the superclass and pull out its method that does that already for us. Okay? So it's very simple. Now, the three methods that are left, push, pop, and top, okay? We have methods to do this as well, okay? But we have to be careful about how we implement them. Because think about our linked list. Our linked list, drew it as a linear object, that it kind of always went this way. But now let's think of our stack as this way, okay? So when I push something onto the stack, it's always going to go here to the top, okay? And when I pop, so that's how I push things to the top. And when I pop things from the stack, I remove it from the top. That's how I pop things. Now, if we were to take this thing and turn it sideways, maybe you could see how we could implement it. And we could turn it, if we turned it this way, or if we turned it this way, it wouldn't matter, as long as we kept our method straight. So for example, if I turned it this way, we would always be inserting to the head, insert to the head, insert to the head, insert from the head. And when we popped it, we'd always be removing the head, removing the head, removing the head. Or if we turned it this way, we'd just be inserting to the tail, and removing the tail. So it doesn't matter. It doesn't matter which one we choose, as long as we as programmers keep it straight. So I say let's do it this way. Super dot insert tail of our data. If we always push it to the tail, we'll consider the tail the top of the list. And to pop it, we'll return super dot, is it delete? Sorry, delete tail. Now this will require a casting to data type T, because we're using generics, okay? So we're inserting to the tail and deleting the tail. Don't forget that you have to put that cast to T there. That way we always keep it straight, that we're always inserting to the front, or pardon me, to the back, and removing from the back. And again, the fact that this is a stack hides that this is taking place. We just push and pop as needed. So now, we also have a nice feature for top. We just returned super dot, and I believe we called it back. And again, this will have to be cast as a T, whoops, as a generic. But you may recall we wrote that method front and back, and all it does is look at what's at the front and back, and it doesn't actually remove it, which is exactly what top does. It just looks at what's at the top of the stack without removing it. So it's super, super simple. Each method just has one line of code. Each method essentially just uses what the superclass has. And now, if we go to main, this stack object is super simple to use. So let's just write a little sample here. Let's make a stack of data type, let's make it integers this time, called stack equals a new stack data type integer constructor. Okay? Now, this will require an import, okay, when you do this. But again, be careful with this, because just like the linked list, there is a built-in stack object in java.util. So once again, I'm teaching you something that you didn't have to learn, because you could have just used the default one. But instead, we're going to import it from our collections, collections.stack. That's our stack that we made our custom one. So that's the one we're going to import, okay? We're not going to use the one that's in the utility library, although I could show you what that one does, and you'd see basically some of the same stuff, okay? So now I can use this object, stack dot, I could push onto that, say a 50. I'll push three things on there, 50, 60, 70. And then I will pop the stack. Okay. And now I should output the stack. Okay, that's one line that's one thing I didn't write. And actually, that reminds me, you guys should have stopped me. When we write a class, there's a couple methods that we should implement. Right? Remember I said that. What were those 4 methods? Clone. You're cheating. You're looking at your code. ToString is, no, not is empty. Destroy. Clone is empty, or clone, destroy, and there's one more. One more that stands to make things, no, we talked about ToString, to make things balanced between one thing and another. Equals, right. So let's write those. Let's do that for good measure. So let's write a public, public string ToString. Okay. So how do we write the ToString method? Well, we could use the superclass. We could return super.ToString. That makes life easy. But think about what the ToString method in linked list will do. If we look at what it did, and where is it? I got to find the crazy ToString method. Here it is. What it did is great. It does output the whole thing, but it uses the word list, which is okay. It's kind of a list, the stack object, but let's change it slightly. Let's add in front of this some words before that this is a stack, and then it'll say list, okay? So that's the only thing we'll add to ToString is that, just so that we know it's a stack, we're going to put the word stack plus super ToString, okay? And then we'll make the clone method. Oops. Which returns a clone, okay, of the current stack object. And again, we could just say return this. That would be, who remembers what that's called? That works. But there's a difference between making a true clone and making kind of a fake clone. Do you remember the words I used? Yeah, a reference. But there was 2 words I used to describe that. And I also used it in terms of searching. There's shallow and the opposite, deep. A deep copy versus a shallow copy. What's this one? Shallow, yeah. That's a shallow copy. Well, let's go with that. Let's cheat a little bit today. Just so, if we wanted to make a deep copy, we'd have to say like stack equals new stack, and we'd have to clone it that way. Or we could call super.clone. Maybe that would be a sort of, actually, why don't we do that? That's kind of a compromise. We'll just clone the superclass. Now, this again has got a problem because it's returning, you see there what it did? It kind of would need it to be a linked list. So it's 2 different objects. So cloning there is not quite as easy as you'd think. So let's just cheat again. Let's just put this. Let's make it a shallow copy. Let's be shallow. Let's be very shallow today. Okay? Now, what were the other ones? 2 more. We did ToString, we did clone, destroy. So void. And let's put final in there. Void, destroy. One of the other reasons, by the way, that you put final in a method, add that qualifier in there, is once you put the word final, it means that that method cannot be overridden. So you cannot, because now you'd think, oh, well, then all I got to do is go super.destroy. Okay? And you can actually see that. I can't zoom in on it, but if you guys look at the light bulb, it says, destroy cannot override destroy in linked list. The overridden method is final. Shoot, I can't do that, okay? I can't destroy, I can't override a method that is already marked as final, okay? So be careful with destroy and that adding that final keyword. It can sometimes throw your logic off a little bit. So you know what? Let's not write that one. Okay? We'll leave that one off the list. So remember I said those 4 methods are a good idea to implement, but not always, right? Sometimes maybe you don't. And we'll also skip equals. We'll skip equals at this point. Okay, so we've got a very simple stack class. Let's use it. Sout stack. So we're going to build the stack. We're going to push 3 items onto it. We're going to pop it once and then output it. Before you run your code, what should come out? What should be on the stack? 50, 60, yeah. Because 70 was the last thing put on, but it's also the first thing popped off the stack. So let's see. 50, 60, good. So we got 50, 60 happening there. Now as well, when we popped it, we returned that. So really we could have outputted that pop. So let's do that. Let's add a little output to that. So when we pop it, it's returning it. So we could actually see, make sure that the 70 is actually being popped off there before we print the stack. We'll run that. Yep, the 70 is showing up there. So it popped it, and then the stack looked like that. So let's do that, those 2 lines 2 more times. We'll pop it and output it, pop it and output it. Okay? And if we take a look at our thing, we'll see it's working. So the 70 was popped, then the 60 was popped, then the 50 was popped, and it kept track that it was an empty list. That worked too. So the stack object has a very simple implementation that you can just push and pop and a few other little features. But what good is it? I haven't proven what good this thing is, like how it could be more useful than a linked list in certain programming problems. Okay? Well, it can. I mean, think of it this way. You guys know about classes, you know about arrays, you know about linked lists. You got a very deep knowledge of dynamic memory management in a computer programming environment. But if I asked you to write a simple program to add 2 numbers together, would you write like a linked list and classes and all that? No, you would probably just use something simple like a couple integers and just do it. You wouldn't need all the functionality that you're aware of. Based on the problem, you would have kind of fit the tool to that particular problem. So the stack fits some problems. Okay? Okay, so let me show you guys a couple more things about stacks just on the presentation side. Okay, so we were able to do what I said we could do. We can create it, push, pop, top is empty in size. We got that done. Okay? What I'm showing to you now is we didn't code this, but this is, I'm just going to dim the lights for a bit here. Sorry, grade 11s. This is what it would look like if we didn't use inheritance. We could create a node, and I would maybe change the name to stack node, and it would be very similar to the linked list node, except I wouldn't need a double reference. So I could just have a reference to the next node. So it's simpler. Create a constructor, override the toString method. Then I would make a stack object. The stack object would just need a reference to the top. It wouldn't need, for example, like in other words, I wouldn't need head and tail. I could maybe just keep track of the top and the length. I could build my constructor. I could write the size method, return the length. I could write an isEmpty method that just checks to see if the length is 0. And the toString method would be, again, very similar code where I just loop through and output it. Again, remember, I'm not using inheritance here. The push method would also be very simple. I'd create a new node, assign its data, which, by the way, I could have done in one method there, but I didn't write an overridden constructor for that class. If it's empty, I would set it to the top. Otherwise, I would just set the top to that node and increase the length. So all the logic got simpler, way simpler. Pop, same thing, much simpler logic. If it's empty, return null. Otherwise, reduce the length, give me the data, move the top to the next reference, and return the data. Very, very simple code. Top, also very simple. So in the notes is an example of how you could write a stack object from scratch without using inheritance, okay? And then the code that would test it, okay? And then the linked list object is the one that I just did that we did together, okay? And there's even an example in the code of that, but we just typed that in, so I'm just going to skip through that. Is it going to work now? There we go. Okay, so finally, why would I need this thing? Okay? Well, there are several reasons for doing this. Okay? As a tool, it's simpler, so it can work on some problems. For example, text parsing. So being able to take text and read through it, which is very common in programming sometimes. A lot of you guys did that for your files problems, where you'd scroll through the text and analyze the text that was coming in. Believe it or not, that's actually how methods work. Methods work on something called the runtime stack, which is essentially how the computer keeps track of method calls. So when it calls a method, it then puts the next method call on top of it on the stack. So say you had this program that said run, and then run called like start, middle, end, and it would keep track of the method calls on something it calls the runtime stack that basically does that. It pops and pushes things onto the stack accordingly, okay? But the one I wanted to show you guys is an interesting one, okay? It's a way to do math that you are not familiar with, but it's the way the computer does, and it uses brackets and braces. So here's a piece of math, okay? Forget computer science. This is just basic math, although you have to change that to multiplication, and that's a division. That's a problem, right? That's a math problem. And you could use BEDMOS to solve this. But the question is there any mistakes in the brackets up there? You look at that. Now, you are just scanning that with your eyes and your brain logic right now. But what I'm going to propose is an algorithm that scans this mathematical equation to make sure that the brackets are nested properly. Which, by the way, is what programs like NetBeans do, right? To make sure your brackets aren't off. But how can we do that? How can we scan this? Well, here's what I'm going to propose. We start on the left and we move towards the right. We will, when we encounter a left bracket or brace or parentheses, we'll put it on the stack. So we'll keep track of that on the stack. When we encounter a right brace or a right parentheses, we will then pop the stack. Okay? And if the pop matches, the two brackets match, then we're okay. But if they don't match, we have an error. Okay? If the stack is empty and we're out of input, then again we have an error. But if the input is finished, in other words, we get through all of these characters, and the stack still has something on it, then again we have an error. Now, if you have been taking a minute to look at that equation, there is no errors in it. Okay? It is fine. But let's try our algorithm and see if it works. So I start my algorithm off and I encounter my first character. It's a bracket. So I'm going to put it on the stack. Okay? Then my next character is a 5. I'm going to skip over that. And then an operation, multiplication. And then I encounter another opening bracket. So I put it on the stack. And then I encounter an 8 and a minus and a 2. And then I encounter a right bracket. So according to my algorithm, when I encounter a right bracket, I look at the top of the stack, and if they match, they're the same type of brackets, curly, round bracket, success, I pop the stack. And now I continue. I encounter a right bracket. Oh, it matches. I pop the stack. Keep reading. Oh, left bracket. Add it to the stack. Left bracket. Add it to the stack. Keep reading. Left bracket. Add it to the stack. Keep reading. Right bracket. Do they match? Yep. Pop the stack. Right bracket. Do they match? Yep. Pop the stack. Keep reading. Left bracket. Add it to the stack. Keep reading. Right bracket. They match. Pop the stack. Right bracket. They match. Pop the stack. I'm out of input. My stack is empty. I have a successful equation here. The stack is a simple way of, for example, parsing through that text and checking for errors. If you were to write an algorithm to do this without stacks and queues, or pardon, without a stack, with just the linked list, you might have too many features of the linked list to maybe accurately do that. It's simpler. It's a simpler algorithm with a simpler data structure like the stack. Okay? Now, let's go up another level. Since we're talking about math, now let me teach you the way the computer does math. Okay? This is the way you're familiar with math. When you see an equation like this, you know how it works. You know BEDMOS says do the brackets first, then do the multiplication, and then do the addition last. And we write it in that format to do that. Why did we put the brackets there in regular math? Why? To override the BEDMOS, right? So that you know that still gets done first. But to a computer, it can write this in a different way where it does not need brackets. This format that you guys are used to, and by the way, most math teachers won't know this because they don't need to know this, it's known as infix notation. So that's called infix notation. What I'm going to teach you are two other ways to write it called prefix notation and postfix notation. The word pre before and the word post after kind of give clues as to how they work. But I'm going to blow you guys' minds today in how math is actually done. So you can write any equation without brackets, and it'll still work. So we'll start with a simple one. 6 minus 1. Okay? And actually, let me launch some notes here as well. I want to make a copy of this. So my apologies. I'm just going to... Okay. So to be clear, an operator performs an operation on two operands. If you think of it in computer science terms, it's like this thing is a method called minus that requires two parameters. And it returns a value. Okay? So an operator performs an operation on two operands. Yeah? But who says we have to write it that way in math? Who says we have to say this operation, this operand, like we can change the order if we want. Why couldn't we write it like this? Okay? Now what does that mean? Well, it could mean the same thing. This is the operator, and these are the two operands. Now the order would matter, but we could also write it like this. Or we could write it like this. Or like this. As opposed to the way we're used to writing it, which is like this. So here are four alternate ways to write the same operation. But what's the advantage to that? Well, there is an advantage to that. Okay? So in... where'd my mouse go? The computer is so slow today. In prefix notation, it's written like this. That's called prefix notation. Okay? In postfix notation, it's written like that. And we know the one we're aware of is called infix notation. Okay? So you can see here that the way it's switched up is fairly simple. Pre means before. Post means after. Okay? But that was a really simple one. Let's try one that's a little more complex. Okay? That's infix. Okay? That's an infix notation. That's the way you guys are aware of it. In math, maybe you'd write it the 2 over here, but it'd be the same idea, right? In prefix notation, it's written this way. Oh, sorry, one more. That's prefix. Now that's really bizarre to know that this and this are the same equation. But how we evaluate it is kind of important, okay? The way it works is using stacks, okay? So the way it works with stacks is you start here and you start reading, and when you encounter an operator, put it on the stack. So, okay, that's an operator. I'll put it on the stack. That's an operator. I'll put it on the stack. Okay? When I encounter two operands, I pop the stack and perform the operation. So 4 and 3, operation plus. What's 4 plus 3? Really? The answer, since this was now just popped off the stack, the answer is placed on the stack. And now I read the next one, 2. Oh, wait, I've got two operators, two operands, pop them and the operation and put the answer on the stack. 7 times 2 is 14. And I have no more input and I'm done. So we'll see how this works in a minute, but this idea of prefix and postfix notation actually allows you to write math equations without brackets. Now, hang on. Where is it? Did I shut it off? I guess I did. Oops. So here it is on the slide again. So there's the infix notation. That's prefix. This is postfix. And here's another one, prefix, postfix. So it allows you to write math equations without brackets. Now, believe it or not, I'm going to teach you guys how to do this. You're going to be able to write these equations. I'll make you a really hard one, and eventually you'll get it. So let me show you the little animation I did to come up with this. And then we got a wrap for today, and I realize I went kind of long today. But I get excited about this stuff. I do. Okay. Here's the example. Oh, we're out of time. That's for tomorrow. Okay, so we started here last time, and we talked about this idea that in basic math, you have the operator, the operands, okay? Two operands with an operator. And then we talked about different ways you can write that. And I described it this way, that this is what's called a prefix expression, a postfix expression, and an infix expression. We are used to seeing our math in this format, okay? But to the computer, it actually prefers one of these two formats, because the result of writing it in those two formats is you do not need to follow the standard BEDMOS formula with brackets. Because here you can see an infix expression, we have to put the brackets there, because if we didn't, according to BEDMOS, we would do 3 times 2 first. We would do this first. So we're using the brackets to override the precedence order, and as a result, do this first. But in a prefix expression, that's not necessary. If we write it this way, and again, you think of it using a stack, the object that we just coded, then it will perform that operation properly. Okay, so remember, here's how it goes. Okay, these items will be all inserted onto a stack. So 2, 3, 4 plus times. Okay, so imagine these objects are all stacked up. Okay, the way it then evaluates this expression, right? Because if we were going to evaluate our top expression using the math we know, we'd go, oh, okay, you go 4 plus 3, you get 7. And then you go 7 times 2, and you get 14. But we'd have to use the brackets to do that math. But with the computer, the way it does it with this prefix expression, okay, is it starts reading from the top of the stack down, okay, like this. And actually, I think I have this stack backwards. Okay, my apologies. 2, 3, 4, yeah. Well, it doesn't honestly matter. Okay? But basically, as it reads, okay, when it encounters a operator, it pops 2 off the stack, these 2 here, performs the operation, Okay, and I've written this backwards. This should be the plus and this should be the times. Well, I'm off today. That's okay. Okay. So it pops 2 off the stack, performs the operation, 3 plus 4, and then puts the result back on the stack. So now our stack would look like this. Okay? And that's just by popping the stack. It then would encounter another operator right here, pop 2 off the stack, do the operation, and put the result back on the stack. And we'd still get the same answer as we got when we did it that way. Okay? So that's prefix expressions. Okay? Kind of interesting. Now I have a little animation that goes with this. So hold on tight. Here it comes. Can't remember if I showed this to you guys last period, but okay. Come on. Come on. There we go. Okay, so here it is. Here it should be. If all is right in the universe. And if this computer goes down today, things are going to be ugly in here. You may hear some inappropriate teacher language. Okay, here we go. So this is a simple one. -6 and 1. So to do the prefix operation, come on, come on. Just one sec. Zoom this recording. Okay. Okay, so here we go. Read from right to left. Okay? Push the operands on the stack. So I push a 1 on the stack, push a 2 on the, or 6 on the stack. Then, the way it works is, when your reading encounters an operator, pop 2 things off the stack and place the result on the stack. Okay? Let's try with a more complex one. With postfix, it's the same idea, just a different order to the algorithm. Okay? So now I'm reading left to right. I push them on the stack. When I encounter an operator, I pop 2 off the stack and place the result on the stack. Okay, let's make it a little more complex. Okay, so with a prefix operation, I read okay? So I'm reading from the right to the left. So I encounter a number on the stack, on the stack, on the stack. When I encounter an operator, I pop 2 off the stack, perform the operation, put the result on the stack. Then I keep reading. Next thing I read is an operator. Pop 2 off the stack, put the result on the stack. I have no more input here, so whatever's left on the stack is my final answer. Watch how it works with postfix. This time I'm reading the other direction. Okay? So now, put that on the stack, put that on the stack. I encounter an operator. Pop 2 off the stack, place the result on this stack. Go back to my inputs. This is a operand, so put it on the stack. Then I encounter an operator. Pop 2 off the stack, place the result on the stack. I have no more input here, so whatever's left is my answer. Okay? There is an algorithm here that we're not going to do, but this is also a way to turn the kind of math that you guys are used to, infix expressions, to postfix expressions. Okay? So I'll leave that to you. It's just something, again, it's just extra there. But this is the kind of stuff you can code, okay? This is the kind of stuff you can, in fact, code. Now, sorry, I'm just turning the recording software back on. Okay, so the Q object, and that's the British spelling for it. For any of you who've been to England or London or anything like that, they use that word, Q. What do they use it for? A line, yeah, it's a waiting line. That's what it means. It's essentially a waiting line. So if you go to the bank in Britain, they'll say, oh, go get in the queue. Whereas here in Canada, we say, oh, go get in line. So it's a line. It's a waiting line. So it is described as a FIFO object. You may remember that the stack was called a LIFO object. The FIFO object essentially means the first one in is the first one out. So let's say I was selling tickets to One Direction at this store right now. Jack Gore would be running to the door right now, and he'd be first in line. Whereas Kyle's a little slower, might wait. Every other one of you grade 12s is already lined up. And Kyle comes in to the end. Who's the first one to get tickets? Jack Gore. Jack Gore is the first one to get those One Direction tickets, and that's what makes it beautiful. All right, so what do we need for a queue object? Well, we're going to need some of the similar things that we needed with a stack object, but again, we're going to change the wording. We're going to need a constructor. We're going to need to add things to the queue, and we're going to use the words enqueue. And then to remove things from the queue, we're going to use the word dequeue. That's the method call we're going to use. We're going to have a front and back method, isEmpty and size. And we're going to do it by inheriting our linked list object. Now, have any of you ever encountered these words before, enqueue and dequeue? It used to be a very popular music software. Used to use those when you'd make playlists. But if you guys use iTunes, they don't use those words, I don't think. I don't personally use iTunes, but some music software used to use those words when you'd create playlists. Okay? Is enqueue it into the list and dequeue it. I think at one time Windows Media Player even used it, but I don't think they do it anymore. But those were words that were actually used. So the programmer's influence was actually showing up in the user side of the software. Okay, so let's do this. Let's get to our code again. So our big example that we've been working on, okay, we did write a stack object. Okay, so we're going to today create a queue object. So add a file to your project, a Java class, and call it a queue. Q-U-E-U-E is the spelling. Okay, and you're going to add that queue object to your collections package. So just like the stack object, it's going to go into collections. So we need a constructor, but this queue object, like the stack object, is type generic, and it extends our linked list object. Whoops. Okay, so just like the stack object, the queue object is an extension of the linked list, so we don't have to reinvent the wheel, and it's generic. So it can hold anything, okay? So this is going to be a great object if at any point in your programming you need some kind of line, okay? That's just a simple line, like just a simple lineup of things. Go with the queue object. It's got the simplicity that you need, okay? Now, like the stack object, we're going to write a couple default methods. So a constructor, okay? And again, we wrote these in the stack object. We're going to write isEmpty and size. Well, here's the good news. They are exactly the same. So if you want, go to your stack class and copy isEmpty, copy size, and you can even copy toString and clone. We'll have to modify them slightly. But I'm going to take toString, size, and isEmpty right out of my stack class into my queue class. Okay, so I have isEmpty, size, toString. The modification I want you to make in toString is just that little thing we did with override. Instead of putting the word stack there, put queue. Okay, so that's the only change we make in toString is we change the word stack to queue, and then we'll just take care of it by its superclass. And then with the clone method, you change the word stack here to the word queue, because that's what we're returning, a shallow copy of our queue object. Is it kind of appropriate today that I mentioned One Direction and the word shallow in one lecture, or did I just insult some of you? I maybe insulted Jack a little bit right there, okay? Maybe, I don't know. You guys don't seem like the One Direction crowd, but maybe I hate to make those assumptions, okay? All right, so that was super easy, okay? Now as well, the constructor is basically the same as well. To construct a class, to construct a queue, I construct a linked list. So all I got to do is make a call to the super constructor. And we're done. Okay? So our super constructor is done as well. So easy. So all we're really left with is the two basic methods to put things into the queue and to take things out of the queue. Okay? So we need a public void enqueue method that takes T data. And we need a public T dequeue method that has no parameters, that will return a value. Okay? These are the two methods we need, enqueue and dequeue. These will both be one line of code, but we have to think it out. In the way we worked with a stack is going to be different than the way we do it with a queue, because of the fact that it's not a LIFO object, it's a FIFO object. First one in is the last one out. Now there's a couple different ways we can write this, but you guys think of how we could write these? Okay, let's take a look at the stack object. When we added and removed from the stack, we said super.insert tail, and when we removed, we said super.delete tail. So we were always adding and deleting from the same side. And by the way, that could have been head and head. Didn't have to be tail. As a matter of fact, Jesse couldn't live with himself. He had to switch it to head because he just couldn't handle it. And I said, I agree with you. I'm good with that. So I'm glad to see you guys are becoming really picky programmers. So how will it look in queue? Well, it doesn't matter as long as we keep it straight. So why don't we think of it this way, that the tail, the head of the list would be like the front of the line. So when we enqueue, we're going to go to super, the super class, and we're going to insert to the tail. So the tail is like the back of the line. So whenever we put something in line, it goes to the back of the line, the tail. But when we dequeue something, we say super dot delete head. So we remove it from the front of the line. And we could have reversed both of those. We could have inserted to the head and deleted from the tail. Doesn't matter, as long as we keep it straight on our end. So the queue object is a much simpler object. It uses our linked list object, so we don't have to do any work, as long as we understand the functionality of the linked list. Okay? And then there was two other little methods that I said we should write, just for good measure. Public T front and back. Front and back. This is, again, like, so this would be the situation that we're all lined up for the One Direction tickets, and say Mika shows up late, and she's not sure if she wants the tickets. She's looking at the line. She could just look at the front of the line without affecting it, so she could see Jack at the front, and she could see Kyle at the back, and she doesn't actually affect the line at all. And then she walks away and goes, wow, and she's stunned by this. So what would the methods be? You guys answer this question. Okay. Well, we actually have a front method already. We built the front method into our linked list class. But is that correct? That would work too. Or we could just say super.get 0. But you know, we already did this. We made a front and back method. So why not just call them? But as long as they are correct, are they correct? Front says the data at the front of the list. The head data, that is correct. That's what we're looking for. So again, this is where, again, you got to be kind of careful about which ones you are using. Super.front and return super.back. Okay? And these are obviously override methods. You are overriding methods that have already exist within the linked list class. So as a matter of fact, it's kind of not something you even need to do because it was already happening. Okay? I'm not returning, you're right. Okay. And this has to be cast into data type T. Okay, whoops. So that's front and back. Very simple methods. And we're done. We now have a working queue object. It has the couple simple methods that we needed to do it. So let's put a test. Let's put it to the test. Let's put the Q to the test. So let's go to our main package and our little main class that we have in our main package. And this was us testing the stack, and it seemed to work. Okay? So I'm just going to delete some of this code and switch the word stack to Q. So Q stack. Now this will require an import. Make sure you are importing it from your collection. So when you go to the import statement for Q, okay, because notice there's already a Q object in the Java utilities class. Okay, so I can import it to from our class. I'm importing our Q object, not their Q object. Okay. You got lost. Okay. So what I've done is I've jumped over to the main class. Okay. And I deleted the code, and I'm switching that testing code to this. I'm going to make a Q with a line of code like this. So I'm going to say Q equals new Q. The light bulb will come up, and it'll ask you to import Q. Okay? Make sure when you import it, you're not importing it from like java.util, that you're importing it from your collections package. Did that help, Mika? Okay. So now let's test its methods. Q dot. Actually, before we test it, let's switch it from integer. Let's do a different data type. Let's do double. Why not? Let's do double. Equals new double. Because again, it's fun to try different data types. We've done string, we've done integer, let's do double. So I'm going to enqueue some data, like 3.14. So I've enqueued this number to my lineup, to the queue. So let me call it again. I'll enqueue another. I'll do it twice, 2 more times. So I'll make this one 4.25, and this one will be 5.36. Oops. I just upped the number each time a little bit, right? So I'm going to throw these 3 doubles into my queue. So again, imagine the way the queue is visualized, right? So it's a lineup. So at the front of the line is 3.14. At the back of the line is 5.36. So if I output the first thing from that queue, if I dequeue, it should dequeue the thing at the front of the line. So I'm going to output q dot dequeue. Whoops. So I'm dequeuing my list right here. So what that should print out is 3.14 because it's at the front of the line. This is very different than our stack object because it would have popped the last item in the list. So run it. Okay, and if all's right in the universe, I'm going to get 3.14 popping out here. Okay? Slow run, but it adds to the suspense of whether or not it works or not. Come on, NetBeans. 3.14. That's what we wanted. Okay? And then let's output the actual list. So we'll S out our queue. Because we can easily turn the queue into a string. So I'll run it again. And here you can see the list. The list is got 4.25 and 5.36. Now remember, this is the front of the line up here. That's the back of the line. As well, when I dequeued 3.14, it removed it from the line. Okay? So now let me try one other little method call. I'm going to try and go S out Q dot front. Now front gives me the front of the line without removing it. So then I'm going to spit the Q out again and make sure that method is working. Okay? So here you can see it spit out 4.25. That is the front of the line, 4.25. So that's right. But then when it outputs the list, notice the list hasn't changed. So the call to the method front looks at the front of the line, but doesn't change the line. But the method DQ gives you what's at the front of the line and actually removes it from the list. They're pretty simple, but I hope you guys understand the difference between those methods. Okay? Kyle. There's another word? It's in the wrong order. Oh, no. Okay, so let's double check. Is your NQ, DQ, and your toString method, it's all the same? Okay, so I'll come over and debug yours in 1 sec. I just want to try and wrap up stacks and queues with you guys. Okay, so in the notes, so I'm not banding you, Kyle. I'm just putting you on pause for a sec. In the notes is an example of code to write the queue from scratch. Okay, so just like the stack object, you can build a queue node. Now, if you build a queue node, it's a good idea to, this time, also keep track of a reference back and forwards, like we did with the linked list. So writing a queue from scratch is a little more work because you'd want to keep those double references in place. But after that, it's not too bad, right? So you'd have a constructor. You can see the constructor is very simple. You might override the toString method. That's pretty simple. Okay, and then the queue object, like our linked list, would use a reference to head and tail. That's easier. It would have a constructor, size is empty. Those would be pretty simple. toString method would be pretty simple. The NQ method is a little more complex than the stack object because, again, you're dealing with two ends of the object, not one end. And same with the DQ method. So we've already written these, so I'm not going to take you guys through the exercise. Know what's in the notes if you need it. Okay? Front and back, also very similar. There's also test code in there that tests both the queue and the stack there. Okay? And then in the notes as well, I also have what we just typed in, the idea of using inheritance to do it. Okay, last thing to cover. What would I use a queue for? Well, I think the queue is probably a little more self-explanatory than the stack object. But the queue object has many uses in computer science. That printer uses a queue. Maybe you've ever seen that on your computer, the print queue. The printer is a lineup. It just keeps track of print jobs as they line up. Okay? Simulations, like doing traffic simulations, obviously with a traffic light, you might need a queue object. Most computers use queues for processing. So they know sort of the order of processing. And that takes us back to the last piece of the IB hardware unit we looked at, that idea of processes lining up. The queue is the object that does that, right? Networking, when you send an email, it's packaged in a queue. So servers dealing with login requests, deal them in order. So queues are all over the place in computer science, okay? What it's queuing and what it's NQing and DQing depends on the problem itself, okay? Probably when we wrote our linked list, you imagined what it was going to be used for was a queue, right? Like it's just this lineup of stuff. But then once we had added methods like insert before and insert after, you kind of abandoned the queue idea because you knew it was better than that. But at its simplest level, a queue is just that idea of a lineup, okay? Now, queues can be varied. And again, this is nothing in the IB curriculum, but you can actually go beyond the queue to something called a priority queue. Now, I've programmed this, and I got the little story to tell you guys about this one. So I'm in computer science, and as you guys can tell, I'm an old guy. And back in the day when I wrote, we had dot matrix printers. Those are the really loud ones that you may still even have one of those at home where it brings a little print head across, goes right? And the university was it was a really old one. So we would write our code, and we were in like a computer lab at the university. And then you'd hit print, and you'd have to go over to this big old printer, and it would print out your code. And it was on those pieces of paper that had little perforations, so you had to like rip them apart. They had little side. Have you guys ever seen these? Yeah, okay. So you know what I'm talking about. So, but the printer was so slow, and there were so many people in the computer lab that you'd hit print, and then you'd have to wait like half an hour because everyone was printing. You'd have to wait like half an hour to see when your thing would come out. It'd be very similar if all of you guys printed like 50 pages right now, and this printer was actually working. You'd all come over and stand here and wait for your particular 50 pages to come out. But this was way worse because it was so much slower. However, what we noticed in computer science was often professors would come down into the computer lab. They'd log in, they'd hit print, and then they'd just walk over to the printer, and all of a sudden their print job would be right there, and then they'd walk away. And we're like, how is that working? Then later, those sneaky buggers made us write the software that did that, and it was a priority queue. And what it was print jobs lined up in the queue, but when you sent your print job, it also sent a priority number with it. So as the printer got there, it went, okay, this is priority 5, so I'll just put it in the line. Oh wait, this job that just came in is priority 1. It jumps, it cuts the line. You guys ever done that at the cafeteria? Hey, can I cut? Well, that's exactly what was happening. The professors, when they logged in, had a different priority than me, and so as a result, their print jobs would cut the line. And they made us write the software that did that. So it was like this torturous thing that happened. Okay? So that's the stack and the queue. Okay? They are actually really useful objects in programming.